Okay, so this is going to be a whirlwind tour through our work. I'm going to combine both talks together because we were short on time. So let me just jump in. So we've been focusing on support for machine learning, both being for programmers and for end users. Yeah, Andrew. And our idea is that we want to put machine learning into every single layer of the stack, but in practice, we've got it at 5 of the 7 layers of the stack. So not all the way down at the sensors and actuators level, and not within our time series data store and controls. So not for controlling access to the data yet. The challenges that we've been looking at in terms of machine intelligence have been in areas of scalability, how to deal with weak, noisy, or sparse labels, and then how to deal with systems that can explain their own behavior. Particularly the more consumer or end user facing systems need to have some ability to explain why they're making the decisions they're making, or users, when they make mistakes, users will abandon them. So at the very basics, we have support for all the basic classifiers as you would expect, and we built a bunch of demo applications that demonstrate these. In the interest of time, I'm going to just move a little bit quickly. We built in support for deep learning. We started with TensorFlow, but realized that that was not the level at which we wanted to engage with deep learning. So we put together a set of these 3-4 systems, NumPy, which is a numerical statistical package in Python, TensorFlow, Keras, which is an open source library that builds on top of TensorFlow, a little bit higher level, and then scikit-learn on top of that. And we put a wrapper around that to make deep learning available within the Giotto infrastructure. Basically says the same thing. We've simplified it to the point where if you're at least somewhat knowledgeable about what you're doing, then we can, for at least a particular deep learning kind of network, LSTM, long short-term memory, we establish a set of parameters that make it very trivial, again, for somebody who's quite knowledgeable, to send in some cleaned up data and be able to come up with some appropriate classification. And we applied this in a couple of different settings. The first setting was to look at classification of aggressive versus non-aggressive drivers. So in talking with various potential partners outside of Google and CMU, an area of interest to a number of our potential partners has been the connected car. So imagine you have your car where you can get data from an embedded IMU, a cell phone, as well as from the onboard diagnostic device. So you have all this data coming in. And I won't go too much into details, but in terms of trying to classify someone's whether someone's aggressive or not, as well as whether an instance of their driving, so a particular trip is aggressive or not, we're in the high 90% in terms of accuracy of that. I was telling Prashant earlier that we've run into problems with Cloud Console and the current state of documentation in Cloud ML, but we're working to get through those issues. Again, in the interest of time, I'm just going to skip past that. So that's where we are for most of the work that we've been doing in terms of the infrastructure, because we've really been focused on, a lot of the work that I've been focusing on has been on this end user support. We've been, on the infrastructure side, we've been very successful, we think, at integrating many of the packages that you would expect, scikit-learn, Cloud ML, to some degree, certainly TensorFlow. All right, in end user support, we've been looking at 3 different ways of providing end user programming. So I'll quickly just jump through each of these. Let's skip through some of this. Basically, our first approach I'm going to tell you about is called Sensors. That was developed by Chris Harrison and Jeff Bigham. And the idea here is to, rather than replicate a somewhat brittle machine vision system, what if you instead leverage the cloud to get your labels and to produce a classifier? So the idea is that at the beginning, you're starting to get, rather than using a machine vision system at the beginning when you don't have very good accuracy, you instead have the crowd label your images for the characteristic that you're interested in, the question you're trying to answer. And that once your training has reached a particular level, you can have the crowd disappear, but you still have the crowd basically answer at specific points, frequent points in the future, so you can make sure that your accuracy has not indeed dropped. And a good example here might be if you're developing is a bus at the bus stop, and you've developed that in summertime in Pittsburgh, and now all of a sudden it's wintertime and you have snow on the ground, you might fall off this cliff in terms of accuracy. So once you've detected that you've fallen off this cliff, you go back up to where getting labels from the crowd, and then you can go back to your machine learning classifier. So it allows you to have the appearance of really high accuracy over time, but not have to have a perfect system over time.
Anind, can I ask a question?
Yeah.
So in the first case, using crowd, and it's a a different sensor from the vision sensor. So
it's using the same image that would be delivered to a machine learning, a vision system, but it's using the crowd as the classifier.
And then when you go into the learning phase, is this like active learning? You go back to the user specifically?
No, so we're looking at active learning. We're looking at this as a classifier that you've trained over the crowd data, that weekly labeled data that you have from before, and that you're just validating that that's correct, but not actually modifying the classifier over here. Although you could imagine you could do active learning. There's no reason you couldn't. It's just that those labels now become much more sparse, depending on how much you're willing to pay the crowd.
Thanks.
Okay, so here's a quick video to give you a sense of how this works. This is a very simple example. So put an old, era 2010 smartphone to the wall, launch the app, select part of the image from the camera that you're interested in, and then you ask a question. The type of question, in this case, you're saying it's a numeric question. You speak out your question, which is, in this case, is how many cars are there in the parking lot? And what you can't see here, what they do? Sorry, revealing all your Roger's secrets. What you couldn't see there is that the second setting that needed to be set was how frequently did you want the crowd to respond? And really, that's a cost metric. Like, how much money do you want to spend on this per month? And then, not surprisingly, the crowd's able to respond. And as you see, it's a little hard to see because it's not zoomed in. But so here, a few seconds later, the crowd starts responding, and there's a little bit of a lag though as this car goes through the lot. I don't know if you can quite see it, but there's a small increase there, and then it goes back down right here. So it's fairly timely, it's very cheap to run, and you can provide you these weak labels on which to build a classifier from. So building from that, we started looking at non-visual based systems, and this is where Yuvraj referred to, and again, I'll skip past a bunch of this because Yuvraj already talked about some of this morning. Built some very simple very simple virtual sensors based on the physical sensors in the room. So with our TI sensor tags, we can do things like, is a window open or closed, is a door open or closed, is someone knocking on the table, and it really just leverages whatever sensors happen to be in that environment to figure out what are the most feature-rich data sources in that environment to make the classification. So user provides the labels, and the system just learns the classifier, produces the classifier. So this is a very, actually, I'm going to skip this video because I think you're going to see the demo out there later. We're also trying to do something similar with the concept of virtual actuators. So you can, right now, our system is set up to deliver content to a specific actuator. We're trying to expand that out to deliver it to a type of actuator. So it's that I want to talk to a light, but I don't really care which light in this room. Or I want to, there's maybe 20 different actuators in this room that have the ability to produce some output. And they might all be of different types of actuators, a screen versus a speaker versus some kind of haptic or tangible device. And really what I want to do is produce a notification, and I might not even care. So it allows the rules and the heuristics that a user might come up with to be much less brittle. Okay, so you've already talked about the content of the super sensor, right? Yes. Okay. So these are still all the same sensors that we talked about. This is what it looks like. And the idea is that we deploy one per room. It's a little bit hard to see, but you can see on the top here, you have acceleration in the XYZ axis, microphone, and EMI. This is only 5 of the 12 sensor streams. This was placed in a kitchen at CMU, and so you can see particular events that are related to the faucet, a urinal being flushed. So some of this was in the bathroom. We do not have urinals in our kitchens, so that would make things much more efficient. Kettle boiling, kettle auto stop. So you can see the characteristics just by eyeballing. You can see the different characteristics of things that you might care about.
Where's your laser cutter?
Not in the kitchen. So you can see the split there. That's where they tried it in a different environment. So I'm just going to jump.
And these are the spectral features, but the spectral as well as time domain features, right? And synthetic versions, min, max, average. There's like a number of streams that are coming out from that same set of sensors.
Okay. So hopefully this won't cause too much feedback from the audio. Nope.
I think I know where.
That should work.
Here is that you have a single sensor placed in the space, and once you with a small number of training labels, depending on the sophistication of what it is you're tracking, you can see down here in the bottom right what's being detected by the system. You can see our HCI skills being put to use.
Yeah, it even does the right and the left faucet.
Yeah.
That's you unmuted?
I totally unmuted. Okay, they're still saying me. Oh,
They can't hear
no,
me?
they can hear.
Okay, all right. So then it got placed in our local shop, and it can detect all of the different tools that are being used in the space as well. All right, so you get the point.
And I think you mentioned this earlier. There's some level of training, right? Just to say this is a hammer, this is a yogurt cup.
It kind of implied that there was some unsupervised stuff.
Right.
The level of unsupervised learning is extremely primitive at this point. It is this sparsely labeled data.
Right.
But it's possible that later when we can do some transfer learning from one to the other.
Yeah, we'll talk about that in a little bit. Okay. All right. So this is actually right here. So we're now, well, related. We're now looking at, and this is very, very simple. So we've gone from something that's much more sophisticated to something simplistic right now, because we're now looking at, can we just identify what people do in a space? So what sensors that they're into, what are the sensor values and what actuation pairs are happening with it. So at a very simple correlational basis, can we produce rules and then suggest those to individuals? So really trivial, every time you come into this room before 9 o'clock, you turn the lights on. Every time you come into this room after 9 o'clock, you leave the lights off. So can we automatically identify those using some techniques that we've been working on with the super sensor to be able to produce a rule? So in this case, I can't remember what this says, a light sensor greater than some empirically derived value, then to actually turn that light fixture on. And again, this is pretty trivial at this point, but we think the idea of being able to make suggestions to people, to end users about what might be appropriate for your new IoT setup or your IoT environment could be really valuable. So it's kind of like what I get from my Tesla or what I get from an Amazon Echo or Google Home, the idea that you keep getting these new surprises or these new value adds because you've already invested in the infrastructure. I'm going to skip through some of this really quickly, as I mentioned a little bit earlier, but really we're using a lot of IoT technology to try and understand people's routines and then provide them feedback to suggest interventions and applications. So I mentioned this morning, how we can use inverse reinforcement learning techniques to be able to learn people's preferences. I can't remember who asked the question this morning, but we do. And so we've been developing a technique for several years now that's a combination of maximum entropy and inverse reinforcement learning to be able to understand and learn people's preferences. Let's skip through all this. That's interesting. So what can we do? Sorry, yeah, I'm happy to go into the math for those who are interested. I'm also conscious that you've used all my time, so
next time round, I owe you.
Yeah, I want to excite you with what we've been able to do, and then we can get into the math if that's what you're interested in. So we've applied this to driving, again, back to the connected car, so we can do things like I've learned how you like to drive. So if you tell me you want to go from here to, I don't know, Castro Street in Mountain View, then it's going to produce a route that actually matches the way you like to drive as opposed to the way Trevor likes to drive. We can control how the automation of a car. So that's something as simple as doing blinking, controlling your blinkers for you, because Americans don't see them. Sorry, never mind. Many drivers don't seem to use their blinkers, and that's a pain. We can also do things like do predictive navigation. So by learning what your preferences are, we can predict where it is that you're going. We can see that an accident might be, or there's some kind of congestion along the way. And even though you're not using the application directly, it can still prompt you and say, hey, we think this is where you're going. We think this is the path you're going to take. We can provide you information about an upcoming hazard that's coming up. Okay, we've applied this to similar to what I mentioned before, aggressive and non-aggressive drivers. So here we can very quickly see this is an aggressive driver going through a particular intersection, speeding through, and then we can show them what a novice or what a non-aggressive driver would do in that same instance, overlaid to improve their process over time. Even if we've never seen a non-aggressive driver behave in that instance, again, we can learn from this class of people that we call non-aggressive drivers and put them in situations they've never been in before. So this is IoT in the connected car. We've applied this to, I'm going to skip this one because we've applied this to a different kind of more traditional embedded system sensing environments in homes. So instrumented pillbox, instrumented telephone, and instrumented coffee maker. And here the goal was to identify, to see how quickly we could identify cognitive decline in an elder who was at risk for cognitive decline but had never actually been diagnosed with it. So they got mainly what you see down here, they got a real-time display about how they were performing these different tasks, how successful they were at taking their medicine, misdialing the phone, and burning their coffee or whatever. And you can see, again, visually, it's easy to see. You can see this is just for medicine taking. You can see that this person, green means they're taking the medicine on time. You can see that there's a little bit mistakes of where there's, when it comes here to mid-September to November, and in the evening medicine, they're doing, oh, sorry, I have that reversed. This is the morning medicine, this is the evening medicine. And you can see in general, this person's doing okay. They had a bad fall over here in January and died when they were part of our study. And it turns out that from just their actions of interacting with the medicine pillbox, we could have identified the fact that they were actually having some significant problems because they actually stopped taking their medicine about a month before they had the fall. So this provides sort of visual evidence that our ability to extract routines can actually be quite useful in a setting like this. Okay, and then something that Yuvraj and I have been focused on, and I was just talking to Prashant about, is that we've been leveraging embedded infrastructure and mobile infrastructure to identify different mental and health states. So we think a big play for IoT is in the health space, and we're looking at different physical and mental states that would be interesting. We have a project that we're looking at to support people with identify Parkinsonian symptoms and severity. We have a project that we've been looking at identifying binge drinking from people's use, just interaction with everyday objects, whether it's a door or their phone, and we want to apply it to student health in general. And so in a week, 2 weeks, we are recruiting 150 students at CMU to wear a wearable tracker, carry around a mobile phone, and be willing to use instrumented artifacts throughout the campus. And we're using it as a study of mental health. And this is actually work that we've been collaborating a lot with Andrew on this. And then earlier work that we're just, well, we won't make the deadline tomorrow, but very soon we'll be presenting or publishing a paper on our ability to detect not drinking, students who aren't drinking, students who are lightly drinking, and students who are binge drinking, again, through their use of this technology. So lots of really cool applications, we think, from this.
What's the sensor you're using to detect binge drinking?
From that one, it's all from your mobile phone. So we're looking at time between key presses. Our initial intuition was that we could look at your gait. And it turns out that when the students, at least the population we're working with, when they are binge drinking, they are not moving. So it's almost the absence of gait. But time between key presses, the number of corrections and insertions, deletions when they're texting, prosody, how they produce speech changes. So we found a good 7, 8 really interesting features that I wouldn't have guessed beforehand. I mean, there's the obvious time of day, day of week, right? It's a college campus, Friday, Saturday nights, that's when the drinking happens. So those are really good features, but that only gets you like 60%. To get to where we are in the high 80%, we have to apply these features that I would never have guessed were relevant. In retrospect, they make sense. In foresight, they did not. So the challenges that we're looking at here, like I said before, are scalability. We want to be able to essentially run our intelligence platform from really the edge, which is at the sensors, all the way up to the end user device, and figure out how to distribute it appropriately and not distribute it in an ad hoc way, but actually come up with heuristics or a parameterized system where this dynamically that the vision can be determined. The way we're dealing with weak, noisy, sparse labels has been really focused on this inverse reinforcement learning technique and routine analysis. And then for intelligibility, we've actually been building a system, which I won't go into detail here because of the time, that helps fairly sophisticated machine learning systems actually explain their own behavior. Really started with some very simple things like decision trees and rules, and really moved them onto hidden Markov models, naive Bayes, Bayesian networks, support vector machines, all with the ability to produce a bunch of different kinds of explanations. So that's where I'm going to leave the machine learning. And that gives me 15 minutes to talk about the end user stuff. Are there any questions about the machine learning stuff that I can answer in 20 seconds?